we're going to talk about Wedges. Wedges. Okay?
Wedges?
No, Wedges. Wedges.
I thought you spoke Spanish, not German.
All right. So wedges, right, are function based on friction, right? And we've been talking about friction, so we might as well talk a little bit about wedges. Okay, so the idea of a wedge is you've got a wedge like this, has some angle, sits on the ground. If you've got a wall here and you push the wedge inwards, right, we're going to push it, what will happen to the block? Right? It's got some weight and it's going to go up. Okay? So the trick with wedge problems is you have to think about what direction's impending motion is. Right? So when we draw our free body diagrams of this wedge, okay, what forces act on the wedge? And most of the time we, by the way, say that wedges are weightless. It's fun to say quickly. Wedges are weightless. Wedges are weightless.
You say with your accent.
Wedges are weightless. Wedges are weightless. Okay? So what forces act on the wedge? Okay, yes, thank you. Friction. What direction on the bottom surface, what direction do you think friction is going to act?
It's opposing the force.
Yeah, it's opposing the force, right? So we'll have the force of friction at A here. What else are we going to have? The pushing force. Anything else?
Weight.
So we're going to say that the wedge is weightless.
Oh.
Okay.
So the weight.
So not the weight. There we go. There's a serious student right there. Friction between the wedge and the block. Okay, and I'm going to call that force of friction at B. Is this all the forces? No. There's no normals, right? So we probably need some normals to have some friction, right? Because we've determined that friction is just a portion of the normal force. So there's going to be a normal at A and a normal at B, right? But remember that the normal is going to be perpendicular to that surface. All right?
So when you put it to the surface it's touching or to the bottom of the wedge?
To the surface it's touching, yeah. Normal forces are always normal to the surface that they act on. Okay, so then if we look at the block, okay, what forces is the block going to have on it?
Friction between the wedge and the block.
Yeah, friction between the wedge and the block. In which direction does that go? Opposite. So it's going to push the block that way. Still be the force of friction at B. What else are we going to have? Okay, so we'll have the weight, sure. The normal at B, says Michael. Agreed. What else? The wall, yeah, the wall is going to keep this thing from sliding, so we'll have some normal at C. How about wall friction? Would it be up or down?
Down, because it's going up.
It'd be down, right? Because it opposes impending motion, right? Okay. Now, it's likely that we're going to get a problem that says something like, how much force do you need to apply at P in order to start moving the block up? What type of problem is that? It's type 2, right? Just always say 2. No, that would be a type 2 problem because it's saying, hey, we're going to overcome static friction in each of these, right? So we know that the force of friction is going to be mu static times normal, okay? We also could have a problem, though, where we says, where we're asked, let's just do problems like that to start with, okay? So, let's do this exact problem actually, and I'm just going to give some numbers to it. Let's say that my block that I'm trying to lift weighs 300 pounds. Okay. And we'll say that mu static everywhere, let's call it 0.25. Okay, for all the surfaces, mu static is 0.25. And we want to find P to move the block up. Okay. So let's write some equations here. We know that the weight here is going to be 300 pounds. So let's see what we know. If we sum the forces in the x direction and set that equal to 0. I probably need the angle of the block, right? What angle does that look like, Preston? 15 degrees. No wrong answer on that question. Looks like 15 degrees. Well, no, there is a wrong answer. Anything over 90, I'd probably call BS on, right?
What about 0?
Okay, so it's 15 degrees. All right, so if that's 15 degrees, then I think in the x direction, does NB have a component in the x?
Mm-hmm.
Yep. How much of it is in the x?
Cosine 15 degrees.
Cosine 15 degrees?
Or sine.
Sine, right? I know. Just think about, do I want the big portion or the little portion of it, right? You know, you just look at it and say, is more of it horizontal or is more of it vertical? Well, more of it's vertical. So I'm looking for the horizontal piece, and if I have 15 degrees, that means sine is going to be much less than the cosine of 15. Does that make sense? That's kind of how, I don't try and do the geometry of these anymore, right? I don't try and work out, well, where exactly is 15 degrees? I look at it and I kind of in my head say, oh, well, there's a little bit of it that's horizontal and a lot of it that's vertical, right? And I know I have this 15 degrees. And so then I think, well, the sine of 15 degrees is going to be much smaller than the cosine of 15 degrees, right? So that's how I know, oh, it's sine 15, because I'm looking for the little piece of it. Maybe that's helpful for you, maybe it's not, I don't know.
I get that.
I think it just became helpful for Travis, maybe. Okay?
'Cause I was picturing it based on the original.
Yeah.
I get it.
Yeah, so I just kind of think, okay.
That's nifty.
That's nifty. All right, so then the force of friction at B, now we know something about this that we can just put right into our equations. We know that the force of friction at B is going to be 0.25 times NB, right? So let's just stick that in right off the bat and say plus 0.25 NB, but what portion of it do we want? Do we want the cosine or the sine of it? Cosine, because we want the big piece of it. Okay. And then it looks like we have NC as well, so minus the normal at C equals 0. So it looks like I have 2 unknowns. Let's keep going. Sum of the forces in the Y has to be equal to 0. So in order for that to happen, NB's got something in the Y, so it's going to be NB cosine 15 degrees minus 0.25 NB sine 15, right? Because now it's just the little piece of the force of friction at B that acts in the Y. Minus the force of friction at C, we know is going to be 0.25 N sub C. Okay, and I'm going to have to go to a second line here, minus 300 pounds equals 0. right? Nothing else. I have 1, 2,
What about the
3,
normal in the
4
Y?
faces
Oh, wait, we have a
in the
wedge.
Y. 1, 2, 3, 4 forces in the Y.
Sure.
Okay. All right. So it looks like with just these, actually, I have 2 equations and 2 unknowns. I can solve for NB and NC. Normal at B and normal at C. Get an answer? What'd you get for NB?
387.
And NC?
193.
Okay. How does this help us? Well, now we know NB that this wedge has to provide. Okay, so now we still don't know P. We need to now put the information we gained from looking at the block into the wedge. Okay, so let's do that. For the wedge, then, we know NB is equal to 387 pounds. Right? Then the force of friction at B, we know, is going to be 0.25 times 387. Right? So we can sum the forces for the wedge at X. Looks like I'll have P minus the force of friction at A, which is 0.25 times the normal at A, minus 0.25, the force of friction at B, so 0.25 times 387 times the cosine of 15, minus 387 times the sine of 15 equals 0. Okay, 2 unknowns still, so I need to write another equation. Sum of the forces in the y. We'll have NA minus 387, right? That's NB, but cosine 15 plus the force of friction at B that's vertical, so that's going to be 0.25, 387 sine 15 equals 0. What'd you find?
I got P is 281. And normal at A is 349. Gonna put it in log.
Anybody else get values like that? Preston did. Josh, you got the same thing? Okay. So why do we use a wedge?
Because it's cool.
I don't know. Because it sounds cool to say a veg. I used a veg.
It might be useful, it depends on the situation.
It depends on the situation if it's useful. How hard did we have to push on this in order to lift 300 pounds? 281, right?
So less.
This veg is not super, it's not a huge advantage. It's a little bit of an advantage. Why don't we try changing it? Rather than having it be a 15-degree wedge, let's make it a 5-degree wedge. And let's see what this force is. So let's go back through. The equations all stay the same. We're just going to change them and say 5 degrees instead of 15. Okay? Can you go back through? Hopefully it's still in your calculator. You can just modify stuff. Got to go all the way back to the beginning and say that it's 5. Okay? And we'll find a new normal at B and normal at C based on 5 degrees, and a new P and a new normal at A. Okay, and I'll put a little 5 subscript underneath these so we know. Okay, so resolve this problem with it being 5 degrees.
So when do you use a wedge?
We'll see in a minute when to use a wedge.
Hey, can you explain the triangle trick again with the angles?
Yeah, so my triangle trick with the angles is when I look at NB here, I realize that the majority of NB is vertical. And typically, with angles that are less than 45 degrees, right, which I know it's less than 45 degrees, the cosine of that angle is going to be larger than the sine, right? And so I say, well, I'm looking for the vertical piece of this, which is big, and so I'd say, oh, that's going to be the cosine, right? Because this is 5 degrees, and so I know that the cosine of 5 degrees is much greater than the sine of 5 degrees, right? And I know I'm looking for the bigger leg, so I say cosine if I'm looking for the vertical piece. Did you get answers, Michael?
Yeah.
What'd you get for NB and NC?
NB was 337 and NC was 130.
Okay. So I guess actually we're going to have to substitute that back in here. That it's not just the angle we have to change in the second one. We have to say that it's actually 337 instead of 387.
Yes.
Right? Went down 50 pounds. Okay.
Oh, interesting.
What'd you get?
For P, I got 195. For FNA, I got 328. If I can read correctly.
Okay. So, when do you use wedges? Well, one time to use them is if you want to lift something really heavy, right? But you don't have 300 pounds to lift this block, you could shove a wedge underneath it and only apply 195 pounds. And it will lift it. Right? So it gives you mechanical advantage. So it makes it, you have to do less work. Well, that's not exactly, not less work in the terms of actual physics, but you have to push with less force to lift it.
Less effort expended.
It's a simple machine, right? Yeah.
Oh.
So this is how you build a pyramid if you ever need to do that without a crane truck. Right? You use a veg. Okay? So what about, what do you think, what role do you think the coefficient of friction plays here? Is it important?
Yes.
Yeah. What do you think the ideal coefficient of friction would be for a wedge? Would it? Okay, so I'm hearing 0 and 1. Michael, why do you think 1?
Because the higher the friction, the less chance of the block moving, because there's going to be less force on the x-axis.
Okay, so the higher the friction, the less chance of the block, like after you aren't applying a load, is that what you're saying? Like when you let go of the wedge?
No, like I'm saying, I don't know how to explain it. So if the friction is higher,
Yeah.
then the block is going to be less likely to move.
Okay.
So you'd be able to push a higher weight.
Okay. So I think, the block would be less likely to move, but it seems like it would take a greater force then to lift the block, don't you think? Right? Because to overcome the friction, you'd need to push harder. Why do you think 0 would be good, Brendan?
Because then it's like really slippery and you could just slide it right under there.
Okay, because then it's really slippery and you could slide it right under there.
Okay.
Let's try it. Let's see what happens. Let's say if the coefficient of friction between everything becomes 0, right? Let's think through this for a second, okay? If the coefficient of friction becomes 0 on this guy, there's no friction force, right? So there's just this normal from C, there's the weight of 300, and there's the normal at B, right? Okay, so let's do the problem with no coefficient of friction. That's probably going to be the fastest way to get to what I want to demonstrate here. Okay, so let's do the problem again with no coefficient of friction. We're going to have the weight of the block is 300 pounds. We're going to have a normal at B, and we're going to have a normal at C, right? Everybody agree with that? If there's no friction on anything, then the sum of the forces in the x direction has to be 0. So I'm going to have NB sine, let's do the 15-degree block, minus NC must equal 0, right? You don't really need to put this in your notes. It's just going to be a...
We're just gonna do it anyways.
Okay, you can put it in your notes if you want. Sum of the forces in the y, I'll have minus 300 pounds plus NB cos 15 equals 0. Okay, so we can solve for NB. It's 300 divided by cos 15. What'd you get? 310 pounds. Okay. So then let's do our veg. Oops. Okay. And on our wedge, we'll have 310 pounds down like this. We'll have our normal was this A, I think? Yeah, normal at A. Okay. And let's just say we aren't going to push on it. Right? We're just letting it sit there. Does it just sit there?
Well, if there's no friction holding it.
Yeah, if there's no friction holding it, no, it does not sit there. What happens?
Sliding.
Yeah, this guy is going that away, right? Because if we sum the forces in the x direction right now and set it equal to 0, right? Well, we can't, because we have 310 pounds sine 15 degrees does not equal 0, right? That's the only thing in the x direction. Okay? So I would say coefficient of static friction of 0 is not good for a wedge, right? Because you're going to have to sit there and hold it the whole time.
That's
Now,
fine.
if you're trying for the least force required to lift it up, maybe it's good there, right? So it depends on our definition of what are we using the wedge for. Are we just using the wedge to move it, and then we're going to like fix it some other way? Or are we going to use the wedge to move it and hold it? And this is called a self-locking wedge,
Like a keystone.
right?
What if you have
Sort of.
a rough surface on the bottom and smooth surface on top?
Okay, yeah, you could have Natasha makes a good suggestion. What if I make my mu static here be higher and this one be lower, right? That might be a good, so that it slides, there's not much force of friction between the block and the wedge. Like maybe we could make this one 0, right? But make this one not 0. Okay, because what we're trying to do is we're trying to move the block up with as little force as possible, but then once we've moved it up, we want it to stay. And this is a self-locking wedge. All right? So if you're trying to figure out, how could you determine if a wedge is self-locking or not?
Friction can overcome the force of the weight, whatever it's holding up.
Well, let's think about it. If we're trying to check if a wedge can be self-locking, what would happen if the wedge is not self-locking? It's going to slide out, which means what will happen to the block? Okay, so here are our two wedges, our wedge and our block, and here's the wall. So if the wedge is about to slide out, where would what direction would the force of friction be on the wedge? Which way is impending motion for the wedge happening? The impending motion is it's getting kicked out, so the force of friction reverses direction and would be in this direction, right? And if it's getting kicked out from the block, same thing, it's going in that direction, so force of friction on the wedge is going to be that away, whereas the force of friction on the block would be this away, right? And the block would be going down, so now the force of friction would be up, right? So this is the force of friction at A, B, and C. Now we compare that to what we did the first time, right? So everything's reversed. All the force of friction are reversed, right? Because what we're checking for now is, will it spit the wedge out? And if it's going to spit the wedge out, right, then these are the directions of the force of friction. So what we can do is we can go ahead and put our force here, P, as an unknown, okay? And let's see if we say mu static for this problem. Let's do the same problem. We'll give it 300 pounds. Let's say mu static is 0.1. Okay? And we're going to go with our theta angle, we'll call it 15 degrees. Okay? So the angle of our wedge is 15 degrees. Our mu static is 0.1 everywhere. So we can go ahead and put our normal at A, normal at B, normal at C. All right. So let's try this again. We'll start with the block first. Sum of the forces in the x has to be equal to 0. What do I have acting in the x? Which one?
Part of the normal.
Part of the normal, which normal?
B.
In B. So we'll have in B, what? Sine 15, yep. Because I'm looking for the horizontal piece, so it's the little piece of NB, so I know it's the sine. What else? Yep. And both these, that one's in the negative direction. This one will also be in the negative direction. And in order for it to slip, we know what type of problem is this? Yep, so it's a type 2 problem. So we know that FFB is mu static times the normal at B. FFB sounds like it's FSB, that's the Russian KGB, isn't it? The new KGB. And all the good movies, right? The FSB agents. No one remembers this? And the Bourne Identity and all that? No, the KGB, that's...
No, KGB
But-
is Russian.
Yeah, but then the KGB went away, and now it's the FSB, isn't it?
I don't even remember. Are we actually? Yes.
Yes, it's important.
Yes, it is.
What is
Federal
the
Security Service of
FSB?
the Russian Federation.
Thank you.
So they call it the FSS.
Federal Security Service, but we call it the FSB.
Probably because Russian and English don't have
Oh,
the same
no,
characters.
because, yeah, it's this funny characters there. All right?
It's probably,
I'm not crazy.
Probably federal security
You're
purpose.
not crazy.
I don't know.
Rolls-Royce, their agents are equipped with water running on vodka.
Okay, here we go. So, FFB, right? FFB. So we have FFB in the negative direction. So we'll have mu static, which we decided is 0.1, times the normal at B, times the cosine of 15, right? What else happens in the x direction? Looks like NC. Minus NC equals 0. Okay. And let's do some of the forces in the y. Set that equal to 0. Okay, so in the y, looks like I'll have minus 300 minus the force, or plus the force of friction at B, at C, so that'd be plus 0.1 normal at B, minus the normal at B, cosine 15, plus the force of friction at B, which would be 0.1 in B. Oops, this should be in C, excuse me. 0.1 in B, sine 15.
Is it NB or is it NC? Wait, no.
This is in C. This is the force of friction at C. So it's 0.1 times n sub C equals 0. Anyone get some values?
Yes. I got negative 308.
Negative 308 for normal at B.
Yes. That's why I hesitated to give an answer.
Ha! That's because, ha!
Flip the sign.
My cuerpo libre. I didn't draw my cuerpo libre. Right? In my cuerpo libre, the normal that acts on the block would be in this direction, right? Right? The force of friction would be in this direction. No, oh gosh.
Come on, you can do it.
if this is coming out, it's going to be, yep, we got that. We had the force of friction correct, right? So I got bit by not drawing my free body diagram again. Does everyone see what happens in this free body diagram where I have them together? I only put normal at B, but that's the normal at B that acts on the veg. The normal at B that acts on the block would be equal and opposite, right? So that changes what? Well, that changes in some of the forces in the Y. Now my normal at B is going up, right? And in the X, my, let's see, my normal at B is also going in the positive X then, right? Force of friction still is going to be negative in the X and so on. Now try that. What do we get?
Positive 298
Yes.
and 48.3.
Okay. So then I have to look at my veg. And I'm going to go ahead and draw a free body diagram of the veg since I screwed it up by not doing that the last time. Okay, so here's my veg. We've decided that we're going to put P as pushing to the right, that the force of friction is actually also pushing to the right. Right? But we know the normal at B is 298 pounds, which means the force of friction at B is going to be 0.1 times 298. Okay, and the force of friction at A we know is 0.1 times the normal at A. Okay. So then, for the veg, I just really love saying that word, veg. I don't know why. Some of the forces in the X. Some of the forces in the X, I'm going to have P. What else?
Both the friction forces.
Yeah, so I'll have P plus 0.1 in A plus 0.1 times 298 times the cosine of 15, then minus something, right? Minus what? 298 sine 15 equals 0. And we can say sum of the forces in the Y is equal to 0. Then I'll have NA minus 298 cos 15 minus 0.1 times 298 sine 15 equals 0. And I can solve for NA and P. So what's it going to mean if we get a positive value for P? And what will it mean if we get a negative value for P?
It's being pushed out and sliding. Would it be sliding if we got a negative value for P?
If we got a negative value for P, would it be sliding? No. If we get a positive value for P, it means that we have to be holding this in at the point it starts to slide.
So negative is good.
So a negative value would mean it's self-locking. A positive value would mean that it actually is not self-locking, that it requires this force P to hold it in place so that it doesn't get spit out, right? Because how we've drawn it is we've assumed that we're applying a force P, yet it is sliding, it's on the verge of sliding out. Yeah.
So if we want to know if it's self-locking,
Yeah.
can we just say that the sine of, or MB sine, whatever the angle is, has to be greater than the frictional forces pushing it, or has to be less than the frictional forces? If you just take the whole P out, right?
But I think it's easier conceptually to put the P in.
Okay.
right? So that we can solve for a value for P and then determine based on it. So what Brendan was suggesting is why don't we just say that the friction forces have to be greater than, what were you saying? The friction force has to be greater than NB?
Yeah, but greater than the sine F.
Greater than the sine of NB.
Yeah.
Right, yeah. So the friction forces would have to be greater than that. And that's essentially what we're doing with finding P and figuring out if it's positive or negative. So what did you find? What's NA and P in this problem?
P, I got 18.8.
18.8.
You got 76?
You got 19. Okay, what'd you get for NA?
295 and a half.
296.
295.5 pounds and 18.8 pounds, right? So this is saying at the point this happens, when it's on the verge of slipping, we have to be applying P, a positive P value of 18.8 pounds. So this says we're holding the wedge in place when it starts to slip out. Okay, so this is a non-self-locking wedge. Right? How would we change that? Increase the mu. Right? Okay.
Increasing the mu would keep it locked.
Would help it be self-locking, yeah. Mm-hmm. Okay. How are we doing on time?
How much self-locking would we want?
How much self-locking would
Like
we
if it
want?
was just negative 0.1, or we want like an order of magnitude more? Is just having the smallest amount that helps? I don't.
Oh, so yeah, so home slice here is asking. Travis is asking, yeah, how much mu static do we want? Like how much extra do we want? Well, we want to figure out. I mean, it depends on what we're trying to do. Are we trying to hold something there in place forever? Then we would probably want a pretty healthy mu static. Are we trying to lift something but have it also hold it? Then we probably want to kind of find that point where mu static is just right, such that it will have the minimum lifting force but still be self-locking.
I guess I meant more like if we had a P that was negative, what kind of P value would we want?
That just so
Would it
if you have
also
a
be
negative
dependent on that?
P value, it just depends. Like how sure do you want it to be that it's not going to move, right? So, all right. So where are we at? We have 10:45. Why don't I have you do a wedge problem here? Yeah, we can do 865. Okay. So very similar to what we just did, but I'll have you work this. Has different coefficients of static friction for different locations. So let's do 865. Determine the smallest force P needed to lift the 3,000-pound load. The coefficient of static friction between A and C and between B and D is 0.3, and between A and B is 0.4. Neglect the weight of each veg. Okay. Did you all get a free body diagram that maybe looks something like this, or two free body diagrams? right, so for the top block, and I think we called it B. Some of the forces in the X, what'd you get?
Normal B sine 15. That's how I started.
So you call, in mine I call that normal A sine 15.
Yeah.
Okay,
Yep.
no, that's fine.
Plus 0.4 times that normal cosine 15.
So that's the friction.
Minus the D, normal force.
Normal D is 0. Somebody else, what'd you get for some of the forces in the Y? Jordan?
I'm checking real quickly.
It's on the page.
Victoria?
The Y?
Yeah.
I got negative 300.
Isn't it 3,000?
I think it's 3,000.
Oh, 3,000.
Yep.
Minus NC times 0.3.
I stick 3.
Okay, minus 0.3. I called it ND, but gotcha.
Plus NE cosine 15.
Okay, and I think that's my NA probably.
Mm-hmm.
Minus 0.4 NB sine 15.
Can't see
Great.
the math, you're off page.
Okay. Did you solve these, Victoria?
No, because I wrote 300 down instead of 3,000.
Well, that's okay. It'll just change it by one digit. So what'd you get for NA and ND? Or, oh,
So for NC,
And D.
or whatever yours is, I got 289.39.
okay.
Then I got 448.53.
Hmm?
Like that,
Oh,
I think. Okay. Fair enough. Okay, so then we can do block A, right? So the equations at A will have some of the forces in the X. So in the X, I'm going to have P minus 0.4 times 4,485 cosine 15 minus 4,485 sine 15 minus 0.3 NC equals 0. And in the y direction, I'll have NC minus 4,485
Can't see that.
cos 15 let's see, in the y, and we'll also have a little bit, so plus 0.4 times 4,485 sine 15 equals 0. Right? We can solve these two. We get P and N sub C. Anyone get values for P and NC?
Yes. 4,054 for P. And 3868 for F and C.
Okay. So this wedge, we're going to have to push on really hard, harder than we'd have to just pick it up, right? This one doesn't have a huge advantage, okay? High coefficient of friction, pretty substantial angle on it. It's going to be more force to push the wedge in than it would be just to lift the block up, okay? All right? So we actually, interestingly, almost never use wedges, right? We don't do that anymore. And the reason we don't do that is because of manufacturing. Okay? Because we invented this thing called the screw. Okay? Now we take something that's round, okay? And what we do is we wrap a wedge around it. You look at the threads of a screw, they go at a diagonal, right? As they come around here. Everybody familiar with this? This is just a wedge that we've twisted into a circle. Okay? So if I were to unwrap one thread's worth, right? So if I looked at this, you know, this continues back around and connects and continues back around and connects, right? It's kind of this helix thing, or it's a spiral, right? If I took one of these from this point here to this point here and unwrapped it, what I would see is something kind of like this, where this is the thread, okay, and this has some angle theta, all right? And what I'm doing when I screw this into a bolt or into a hole that's threaded, I'm putting essentially a little block that rides along this ramp, okay? And as I twist the screw, this block rides up the wedge, okay? And the way that happens, if I apply to my bolt, oops, I apply a moment, okay? Remember, a moment is equal to a force times a distance. I think this pen is on its way. It's not very good, so I'll switch back to red. Right? A moment is a force times a distance. Okay? So what happens is, if we turn the screw, we get some force that's the moment over the radius of the bolt, right? So this has some radius. And so if I apply 10 pounds, right, at 1 inch out, I have 10 inch-pounds of moment. But if my bolt, say it's a, let's say it's a half-inch bolt, right? That means its radius is only 1/4 of an inch. So 10 inch-pounds becomes, to get that same moment of 10 inch-pounds, what would my force have to be, you know, right there, tangent? If I need to generate 10 inch-pounds of moment with only a 1/4 inch radius, right? We're saying this is a half-inch bolt, right? And so the radius is 1/4. I need my moment, 10 inch-pounds, to equal some force, but I know the lever arm is just 0.25, right? So F has to equal 40 pounds. Does everyone understand where I'm getting 40 from? Mm-hmm. Okay? And that would be the force that's going against here, right? That's the force that if I'm riding around on the edge of my bolt, I'm generating a force of 40 pounds when I apply 10 inch-pounds. So in kind of the derivation that follows, I'm going to put the force that's pushing us up the ramp as M over R. M being the moment, the twisty force that I'm putting on there, R being the radius of the bolt. Okay? Now, also on my little block, and maybe I'm going to just make this drawing bigger of my little block that's going up the ramp. Okay? So we've got my M over R. We'd have some normal from the ramp, right? Or normal from the screw. I'm going to say ramp. I should be saying veg because I like saying veg. We'll have, what else will we have on this?
Friction.
Yeah. We'll have some friction force. Okay. And then we'll have, maybe the nut is applied, has some weight that it's moving, right? Maybe it's the jack on our car. It's just a screw jack. You turn that screw. Well, the thing that you're moving up, right, has the whole weight of the car on it, or the weight of one side of the car on it. That's our weight here. Okay? So we've got weight, we've got moment. This looks just like a ramp problem, doesn't it? Yeah, you betcha. We're going to do something a little different, though. We're going to go back to saying that this is the resultant, right? And remember when we first started talking about friction, I said that this angle here was the friction angle. Okay? The angle that the resultant of the combination of the force of friction and the normal makes is the static, is phi, the static friction angle. And then we could see that this angle here that goes from the resultant to there, we're going to call that, no, I did that wrong. I kind of boogered this up. This angle here, this little angle, that's just theta, right? Between the normal, the angle between the normal and this vertical line. This is my normal force. I find if I make the lines thicker, it makes it make more sense, right? Okay. So the angle between the vertical and the normal, well, that's just the theta of my ramp, right? That's theta of the ramp. And then phi is the angle between the normal and the resultant. This is the friction angle here. Okay. So in the case where we're trying to, impending motion is up, I'm trying to push the screw up the ramp, right? So I'm jacking my car up. We could write the sum of the forces in the x and the y here. So sum of the forces in the x has to equal 0. What do we have acting in the x? Well, we'll have m over r. We'll have r, which is the resultant of these two forces, and it's going to be sine of phi plus theta. And that's going to equal 0. Those, if essentially what I'm doing is I'm combining the normal and the force of friction into this r. So there's only 3 forces to consider. The moment, the force caused by the moment, the weight, and then the resultant of the normal and the force of friction. Okay? Then let's sum the forces in the y direction and set that equal to 0. In the y direction, I'm going to have the weight, negative. And I do have quite a bit of r, so I'm going to have plus r, and it's going to be the, let's see, the cosine of phi plus theta equals 0. Okay. If I solve these two equations simultaneously, I can come up with, for the moment, I come up with this one.
Can't see that one.
Little r. Because the big r's cancel. Right? When I turn it into tangent, the big r's cancel. And I end up with the moment required for upward motion is just the radius of the bolt times the weight times the tangent of the friction angle plus the pitch or steepness of the ramp. Okay, so theta, remember, if we go back, is how steep the ramp is going up. Phi is the friction angle, right? Which is just tan phi is equal to mu static. Okay? And so we end up with a really simple equation for if I'm trying to move something up, I know its weight, I know the radius of the bolt I'm using, I know the coefficient of static friction, and I know the pitch of the screw. or how many revolutions per inch, I can determine the required moment to lift it. Sorry. Got carried away with my equals to 0 there. Okay. So this is section 8.4. What I just did is this is upward impending motion. This is when I'm pushing it up. If I switch, right? What about if I'm going down? We have the same idea of a self-locking screw, which is like a self-locking wedge. And we have to decide, is theta, the steepness or the pitch of the screw, greater than phi static, or is it less than? And that changes our equation slightly, okay? And this has to do with whether it's self-locking or not. So self-locking is phi static is greater than theta. So the coefficient of static friction, the inverse tangent of that, is greater than theta, okay? I'm not going to put these on the exam, okay, because these are just a simple look it up, plug and chug type problem, okay? But I just wanted to explain to you, wedges will be on the exam. And the question is, but wait a second, Andy, we never use wedges. You're right, but we use screws all the time, okay? We use screws all the time for stuff to apply forces, vices, right, jacks. All sorts of things use screws, which are essentially just wedges wound around a cylinder. Okay, so these equations, you don't need to commit them to memory. I'd like you to work a few problems with them so that you get used to them. I will not be quizzing you or testing you on an exam on them, however. Just want you exposed to them, because in machine design, if you're a mechanical engineer, you'll do this a lot. Okay, so it's going to be really important to know that, so you're exposed to it.
But basically, once you know how to do wedges, then it's simple, right?
Well, yeah, basically once you know how to do wedges, it's simple, but it's even more simple than a wedge, because you can just use an equation, right? Which is what really happens a lot as you go further in engineering after this year, is you start getting equations that rely on the fundamentals that we've learned now, but you never really use the fundamentals as much as you use the equations that are built upon the fundamentals, right? No, it gets hard because your professors make you derive those, but then once you actually just have to apply them and use them, the actual practice is easier than the schooling. Does that make sense? Okay. So I think what I want to do, I've been doing some soul searching about how to wrap this class up. Chapters 9 and 10 really are prep for dynamics. Okay, they're about finding the the area moment of inertia, which we'll use next term and in dynamics. However, I'm just going to reteach it next term and again in dynamics. And so I would rather spend the remaining time in the class making sure you have really good chapters 1 through 8. And so next week is going to be kind of a dead week, in that I'm not going to give you another quiz, and I won't be giving you any more homework besides what I posted yesterday afternoon, which is a wedge problem. That will be your last homework assignment. What I plan to do on Monday is provide you with a packet of problems that cover kind of the breadth of what we've covered in this class, okay? This will not be, I just want to be really clear, this will not be a study guide for the final, okay? Because I don't want you in any way to construe what is in the packet is the only thing I'm testing on, or I'm testing exactly on a problem that looks just like this. The packet is for me to go back and say, okay, we've had some pretty poor performance on midterms so far, and I want you to nail it on the final, okay? I'm not going to change how hard my final is or how hard my midterms were. Those were appropriate level of exams for this class. It's why I don't curve, because I feel like in order to be effective and to go on, you need to know this material, right? My exams aren't perfect, I understand that, but they're good enough, okay? And so my final exam will be like those. It will be good enough. It won't be perfect. But what I want to do next week is a solid review. Every day, we're going to be doing a solid review of chapters 1 through 8. Okay, and I'll provide you a packet that has some problems in it. We can work through them together. If you have stuff that you think of over the weekend, man, I really struggled in this section, email me so that I can make sure and include some good problems that stretch you in that area. Okay? So that's the plan for Dead Week. Never done this before. It's a new experiment. All right?
Do you go over